S goes and you look at the composition, then if you tensor it with the differential module of class no more than S, it still is a ghost. Yeah? So this gives you a way of testing that the class of something, if the class of something is less than or equal to a given number S. You'll see how it comes up. I mean, this you're familiar with already in the world of complexes. If you have a map between complexes which is 0 on homology, tensoring it could change it. Tensoring with the complex could change it. So let me just quickly explain the proof of this result. It's not very difficult. It's in fact the obvious proof, namely an induction on class. On the class of F. So what's the basis? So the basis is, suppose the class is 0. What does it tell you about F? So if you think about the definition, it just means that F is a projective module with no differential. Right? Hence, now you see the composed, in fact you can look at any step. If you look at this, xi to xi minus 1, so this is a ghost, implies it stays a ghost after tensoring with P, tensoring with F. So in this case, the box tensor is nothing but the usual tensor, and it's just a projective module with no differential. So you can take the module outside the tensor homology. So it's still a ghost. So each ghost, when you tensor it with a projective module, stays a ghost. You can, for example, you can test it by looking at free modules, because projective modules are direct summands of free modules. And then you can test it for free module of rank 1. But then it's just the same map. So this is a triviality. And in general, it's the obvious, as I said, it's an obvious induction. So induction step. So we know that it has some filtration. So it has, you have a filtration, we have a filtration of F, and so we have an exact sequence. So this is a flag. So one has an exact sequence like this. And the quotient, let me write it as Fn, and this is just a projective module. So we have exact sequences like this. So these are differential modules, but this is just a projective module with zero differential. So now, so you see what you have is, let me not make a mistake with so we have, and then you also have this xn minus 1 to x. So this is Vn, and this is a composed map from xn minus 1 to x. So these two give you some kind of a ladder. So we have xn. If you tensor this with xn, you get Fn minus 1. Because this is an exact sequence, and if you forget the differentials, these are projective modules, so tensoring keeps them exact. And you get an exact sequence of differential modules, and exact sequence of differential modules, when you pass to homology, gives you long exact sequences like for complexes. So what you can do is, so you get a sequence like this, And then you fill in the ladder coming from here. So it's this to Fn, and then this one. And then finally this. I should say this is a very standard calculation, and this is the same calculation that goes into all proofs of the Gauss lemma in any context, more or less. Okay, so we have a diagram like this. We are trying to analyze the map from this one to here, x tensor Fn to x tensor Fn. All right, so the induction hypothesis tells you that this is a ghost. So this map is 0 by induction. Okay. Now, this map is 0 because Fn is projective. Because of this. Fn is a projective module, and the map from xn to xn minus 1 was a ghost. Now, it's a standard diagram chase to see that if you look at this map, this is 0. Yeah? It's really a standard diagram chase. It makes sense somehow because the building blocks, well, this is a bit of a lie, but the building blocks, you see, going from here to here, from here to there, you can go from here to there, which is 0. And going from here to there, if you go from, rather, yeah, the map from here to here is 0. So this map turns out to be 0. That's not quite correct, but it's not hard to check, given that this is 0 and this is 0, that this composite is 0. All right? So that's the proof of the Gauss lemma. It's really not it's a fairly straightforward proof. Okay, and as I said, the way I understand this lemma is that it gives you a way of checking that the class is no more than something. It gives you a way of proving that the class must be at least something by constructing complexes that violate this thing here. So this is the next step. So now the proof of the class inequality. All right. So the standard reduction, again, basically localization, brings you to the case where you have a local ring. That means that M is the unique maximal ideal of R and K is the residue field. And you can assume that also that, and this is the crucial bit, that the length of the homology of D is finite and it's non-zero. So remember, one part of the inequality, on the one side we had the height of the annihilator of H of D. I can ensure that it's the radical, so the annihilator. If you look at the radical, this is just M. That's the point of this step. Yeah? And we want to prove, need to prove that the class of F is at least the height of the annihilator, which is of course the dimension of the ring. Right? So the proof is as follows. So we want to construct, I'll construct a chain of complexes for which this property is violated for F. So I want to use the Gauss lemma. So the first step